Welcome to this IPCAI presentation on the topic comparing the effectiveness of augmented reality-based and conventional instructions during single ECMO cannulation training. My name is Julian and this work was co-authored by Viviane, Maximilian Halbe, Francesco Maisano, Quentin, Lohmeyer, and Mirko, Mebolt. Extracorporeal membrane oxygenation is a life-saving procedure for severe respiratory or cardiac failure, and it has evolved from a last resort treatment to more mainstream therapy over the last few years. However, mortality rate still stays high at above 60%, and sufficient training has been shown to be key to reducing these mortality rates. Also, high-fidelity simulators have been developed with very promising results. On top of that, augmented reality has started to emerge as a training tool in recent years, offering fundamentally new possibilities to visualize and interact with digital content, and devices are now accessible on the market at affordable prices. However, only a small percentage of AR projects have dealt with training procedures, while most of them have been applied to actual treatment scenarios. So the question arises, can we further improve training outcomes by using augmented reality compared to conventional training instructions? And there has been related work from Asmi et al. They also compared the effectiveness of AR-based instructions provided by an OST HMD to conventional training instructions. And they found that participants spent more time training, but were faster in completing the procedure during the assessment run. And they also found the work with OST HMD more engaging and reported high levels of confidence. In this work, we want to extend this research to ECMO cannulation training, to also compare AR instructions versus conventional training, regularly performed at the university hospital. And besides training times and user experience, we emphasize a detailed error analysis. Fewer errors during the training are expected to lead to fewer necessary training iterations and also less supervision needed to learn the procedure. We see two chief advantages of AR step-by-step instructions. First, the learner's access to contextual information. So all the available information is really reduced to manageable increments, and the proximity of information. So participants can check what they are doing, their execution against the tutorial in real time, and they can adjust their behavior accordingly. To compare both instruction types, we recruited 21 medical students, third year and fourth year medical students. We split them into two groups. Both performed two procedures. The A group first performed conventional, then AR guided procedures, and the second group, the B group, vice versa. The first procedure included disinfection and draping and distal perfusion cannulation, and the second procedure included venous puncture and venous cannulation. Participants were wearing a HoloLens, Microsoft HoloLens 2 during the studies for the AR instructions. So we started the whole setup by giving them an introduction to Microsoft HoloLens 2. Then they filled out previous experience questionnaires and performed the two procedures. Before each procedure, they watched a video showing all steps to be performed. And after the procedure, they filled out a user experience questionnaire. Here you can see the whole setup. So we have the simulator. Next to the simulator on a table, we have the tools, also with labels for procedure 1 and 2 on the respective side of the simulator. And we also have a computer to fill out the questionnaires, and for the conventional training instructions to watch videos of certain steps. Just on the left-hand side of the simulator, there are also paper instructions placed on a table, which you cannot see here in this photo. The AR step-by-step instructions look as follows. It's a text-based guide that includes images. By pressing on an image, it actually is scaled up. Then there are videos, and only for two sub-steps, we also show simple 3D models. The conventional training instructions use both paper documents and videos that can be watched on a computer. And the text, the images, and the videos are exactly the same as we use on the AR step-by-step instructions. Whenever there's a video available for a certain sub-step or step, this is like shown here by red video sign. So then participants can actually go to the computer and watch the video if needed. We measured training times. We derived a detailed error protocol where each sub-step or each error for a sub-step is ranked by severity with a factor between 1 and 3. So 1-point error is a small error without impact on further steps. 2-point error is a larger error that has an impact on further steps. And the 3-point error is either a skipped step or if the maximum time for a step is exceeded, which then leads to incompletion in our analysis. We further categorize all errors into either handling or knowledge-related errors, or possibly both, if we could not clearly distinguish them from one another. Finally, we evaluated user experience questionnaires. So this is a standardized questionnaires with 6 categories or scales and 26 questions. You can see the full user experience questionnaire here on the right side. It uses a scale ranging from 1 to 7, and during analysis, this is then rescaled to range from -3 to +3. Now looking on the overall results in terms of training times and errors for both procedures. So the left chart shows the training time, the right chart shows the error counts, always for P1 and P2. And here in blue we have augmented reality instructions. In orange we have step-by-step instructions, conventional step-by-step instructions. And what we can see is that for both procedures, training times were slightly higher with augmented reality. But looking here on the second procedure, also the spread and the variances were considerably smaller when using augmented reality. For error counts in the first procedure, they were quite similar, slightly reduced for augmented reality instructions. And for the second procedure here, we really see a significant difference between error counts, and also very considerable difference in the variances between augmented reality and conventional instructions. So how did we come up exactly with these numbers for the error counts? Here I would like to show you the, very small, but this is the full error protocol that we derived for the second procedure. And here we can just have a look on a small excerpt of it. So here in the header, you see the error description, then the severity ranging from 1 to 3. And now each of these columns represents the results of one participant. And finally, the last column shows the categorization into either knowledge or handling related errors, or possibly both. So to calculate this total error count, we sum up all the errors in each row. We multiply them by the severity factor and get an intermediate result here. And this is then summed up over the whole column to get us the total error count. And what is interesting, we also found some differences in handling related errors, but most present, we saw a 66% reduction in knowledge related errors when using augmented reality. So really a very clear result here on the knowledge related error side. For the user experience questionnaire, here we see on one axis the 6 categories and the rescaled point ratings from -3 to +3, again, proof augmented reality, and orange for conventional instructions. And except for dependability, which was pretty much similar ranking, slightly positive, we see that augmented reality performed significantly better in 5 out of 6 of the scales used in this question. So what we just saw in these results is that, first of all, P1 is clearly less complex than P2. This matches also with the interviews, because participants stated they could perform most of the steps of P1 just by remembering the steps from the video they watched before and without consulting the instructions. In contrast, for the second procedure, we saw significantly less errors and better ratings in 5 out of 6 of the scales in the questionnaire when using AI instructions. And we could observe that with augmented reality, the instructions were consulted on a regular basis, which was noticeable by either a brief interruption of the hand movement or by a slight shift of the head to the side. And with the paper-based instruction, like with the conventional instructions, they were only consulted a few times during the procedure, but each time for a longer period. And so these differences in instruction types resulted in a reduction, in a 66% reduction of knowledge-related errors. And this supports our initial hypothesis about the benefits of having access to contextual instructions in close proximity. Also, when we compare these error counts with the user experience ratings, this indicates that these ratings were not only due to the more motivating and exciting work when using OST HMD, but also due to the better information display. To conclude, our work extends previous research on AR step-by-step instructions to ECMO cannulation training. Also, our results show promise for using AR in surgical training scenarios. We observed considerably smaller variances in errors and training times, and we think this might help to standardize training performances in the future. And we think this will also make training outcomes more predictable, which is a huge benefit for trainings. The main limitation of our work as it stands is that we only investigated one training iteration. So further studies are needed to assess how this affects physicians' long-term knowledge and skill development. So for now, we can only say this, how this performance looks after one training run. With this, I'm finishing my presentation, and I thank you very much for joining.